Good morning, sir.
Are you able to hear me?
Yes,
Okay.
sir.
So in the last class, we started with module 3,
Yes, sir.
optimal system operation. I hope you understood what is the main aim of optimal operation. Basically, it is to reduce the generation cost. So if it is generation cost, we already talked about the total cost. It was nothing but a summation of capital cost, operating cost, and maintenance cost. So capital cost was one-time investment, so need not to be worried about. Then we had maintenance cost, which is a day-to-day routine, and it is negligible compared to capital cost. So that is also not to be accounted. So ultimately, we are going to concentrate on operating cost, which is nothing but the cost incurred on the fuel. And whenever we talk about optimal system operation, we are concerned only with thermal and diesel plants. Because when it comes to hydel power plant, you know that the water is available free of cost. Only thing is it is seasonal in nature. So we are specific only to thermal and diesel plants, where we'll have to invest on diesel as well as coal. So our ultimate intention is to reduce the operating cost. This is what we talked about in the last class. Then we went on with performance curves. What are the 3 performance curves that you have understood?
Input output
What are the 3
curve.
performance curves?
Input output curve.
Okay. Heat
And
rate
then
curve, and then
heat rate
incremental
curve.
cost curve. Yeah. Okay. And also you talked about incremental fuel cost curve. So what do you mean by incremental fuel cost?
The additional
Incremental fuel
power.
cost. This term is very, very important.
The additional power generated. The cost for the power.
To generate the additional power, you need to invest additional money. That is nothing but cost. Exactly. So that is your incremental fuel cost. And before continuing further, in case there is a break in my voice, please message me immediately. Is that clear?
Yes, sir.
Shall we continue?
Yes, sir.
Shall we continue?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Anybody? Shall we continue?
Yes, sir.
Are you able to hear? Okay, fine. Then in the last class, we started with the idealized case derivation, which was economic generation scheduling, neglecting process, and okay, economic generation. Okay, economic generation scheduling, neglecting losses and generation limits. So initially, we have represented the power plants. Those circles represent the power plants, and C1, C2, C3 represents the respective cost involved in generating the power, and P1, PG1, PG2, PG3 up to PGN represents the power being generated by the respective plants. And then on the right hand side, ahead of the bus bar, you can see the load demand that is being fed from these set of units. So then we started with power balance equation, which was total power generated is equal to total power being consumed plus power wasted in the form of losses. So it is written as summation PGI is equal to PD plus PL. PD is nothing but power being drawn by the consumer. PL is losses. Since this particular derivation is an idealized case, we consider that the losses are 0, so PL will be 0. So you are left out with summation PGA is equal to PD. In the next step, we try to rearrange this equation. So if you rearrange this, you have PGI minus PD is equal to 0. And we call this equation as equality constraint equation. Then after this, we talked about aim of economic dispatch is to minimize. I hope it is clear so far. Is it clear? Please respond so that I can continue.
Yes, sir.
Yes, sir.
Is this clear
Yes, sir.
till here? Hello?
Yes, sir.
Okay, fine. Okay, in the next sheet right now, we are defining a function called Lagrangian function. I think this particular image looks little blur. When I'm sending you the hard copy, I'll see to that I'll take a proper image and I'll send it. We are going to define a Lagrangian function or multiplier, and this Lagrangian is given by function to be minimized minus lambda into equality constraint equation. This Lagrangian function already you would have studied in your engineering mathematics. I don't know whether it belongs to M2, M3 or M4, but Lagrangian is already defined. Same thing, we are using it here in power systems. So I repeat the definition: Lagrangian function is equal to function to be minimized minus lambda into equality constraint equation. So lambda is basically a variable here. Equality constraint equation already we have defined. Function to be minimized is nothing but cost. So I am replacing that by the variable. Function to be minimized is replaced by C subscript T, Ct, minus lambda into summation PGI, summation I varying from 1 to n PGI minus PD, which is equality constraint equation. So Lagrangian is equal to Ct minus lambda into summation PGI minus PD. Now, in order to get any minimum function, we always tend to take first derivative of the function mathematically. Same thing we have to do here also. Ct, if we see, our intention is to make Ct total cost minimum. If that Ct function has to be minimum, LHS Lagrangian also has to be minimum. I repeat, if the total cost Ct variable on the RHS has to be minimum, LHS variable Lagrangian also must be a minimum function. Mathematically, whenever you are going to define a minimum function, it is nothing but first derivative of the function is equated to 0. So first derivative of Lagrangian with respect to PGI is equal to 0. So d Lagrangian by d PGI is equal to 0. Now we tend to differentiate that. So if you differentiate that, on the LHS you have differentiation of Lagrangian with respect to PGI equal to dCt by dPGI minus lambda. Lambda is a constant value basically, multiplied by, you have summation I varying from 1 to n PGI. If that is differentiated with respect to PGI, you get 1 minus dPd by dPGI. I am going to differentiate PD, which is the demand, with respect to PGI. Demand basically will be constant at any point of time. So whenever you differentiate a constant, you get 0. So ultimately, the equation reduces to dCt by dPGI is equal to lambda into 1 minus 0, which is nothing but 1 itself. So dCt by dPGI is equal to lambda. This equation is called as coordination equation. This is very, very important. This is called as coordination equation. Am I clear till here? What has happened in the derivation? Please respond.
Yes,
sir.
Yes.
Okay. So rather than this equation what this equation conveys is very, very important right now. dCt by dPGA is nothing but differential of the cost. This is equal to a constant parameter. And this expression, see, I have written dCt by dPGA CT means total cost. With respect to individual plants, if you consider, then it will become DC1 by DPG1, DC2 by DPG2, DC3 by DPG3 up to n plants is equal to lambda. Always remember the first derivative of the cost function is always your incremental fuel cost equation. If you do you remember this? In the last class when I was defining about the incremental fuel cost curve, I had given two equations. One is cost equation, the other one is incremental fuel cost equation. Incremental fuel cost equation we had got by differentiating the cost equation. That was nothing but dC by dPGI. Do you remember that? So dC by lambda. So what do you understand from this final expression? Lambda is a constant. dC1 by dP1 is equal to dC2 by dP2 up to n plants. What do you understand by that? What do you understand by this? Please talk. Are you able to hear me?
Yes, sir. I
Hello?
didn't get what are you trying to ask? I didn't get that.
Hello?
Hello?
Sir, your voice was breaking in between, sir.
Hello?
Yes, sir. Like, I'm not getting like
Are
what
you
are
able to
you
hear
trying
me?
to ask me? Ask us.
Is my voice
Yes,
audible
sir.
right now?
It's no audible.
Okay. Till where was I clear? Okay.
Yes,
Till where
sir.
was it clear?
Like in between, it's breaking. So,
No, no. No. Till where was the voice clear? No. Till where was it clear so that I can repeat the. Till where was it clear?
That coordination
No, no, no. In between it was
equation.
breaking, but till which part it was absolutely fine.
The coordination equation.
Differentiation part, was it fine? Okay. Okay. Fine. Right. So
Yes, sir.
now am I
yes,
audible?
sir,
Shall I
you are.
continue? Sir. Now am I audible? Shall I continue? Okay. 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 Yeah. See, dCT by dPGI is equal to lambda. This is basically the coordination equation.
Yes, sir.
We have taken Lagrangian function, which was nothing but CT minus lambda in equality constant equation. We have taken the first derivative. Then after simplification, we got dCT by dPGI is equal. Hello, am I audible now?
Yes, sir.
Sir.
Hello.
Sure.
Okay. Yeah, the last question that I asked was dC1 by dP1 equal to dC2 by dP2 for n plants is equal to lambda. What do you understand by that? Are you there? Hello.
Yes, sir.
Yeah, what do you understand by that? What is dC by dP? What is dC by dP? What does it represent? In the performance curve, we have studied about it. It is basically incremental fuel cost. Is it not? Hello?
Yes, sir.
Okay. So
Okay.
from this expression, we can understand that in order to go for economic operation, all the plants must operate with equal incremental fuel cost. If you operate the plant at equal incremental fuel cost, then only you will be getting optimal operation in case 1. Is this clear?
Yes, sir.
Okay. See, in the performance curve, if you remember, you have studied the cost equation. Then, if you take the first derivative, you have got incremental fuel cost, right?
Yes, sir.
Yes, sir. Okay. So here we have got the same dC1 by dP1, dC2 by dP2 for all the plants being same means try to operate all the plants at equal incremental fuel cost. I already told you what is incremental fuel cost. If you try to operate all the plants at the same incremental fuel cost, then you can reduce the overall operating cost. That is the theme of this particular derivation. Is this clear? Is this clear?
Yes, sir.
Okay. Many a times this derivation will be asked for 6 to 8 marks in your examination. Anyway, I'll be sending the material, not to worry. Shall we continue further?
Yes, sir.
Okay. Now here, we have finished the derivation. Before starting with the problem, we again reconsider the cost equation, which is CI is equal to half AI PGI square plus BI PGI plus DI. And we rewrite the incremental fuel cost equation, which is dCi by dPGI is equal to AI PGI plus DI. So here the second equation we have got by differentiating the first equation. Now we bring in coordination equation here. I hope I am audible. Hello?
Yes, sir.
You're audible.
Okay, fine. The third equation is coordination equation, which is dCi by dPGI is equal to lambda. Now we try to substitute second equation in third equation because for the second and third equation LHS remains the same. So it becomes lambda is equal to AI PGI plus DI. Is that clear? Equate equation 2 and 3. If you equate equation 2 and 3, RHS will be same. So you get AI PGI plus BI is equal to lambda. Rearrange the same. You will be getting PGI is equal to lambda minus BI by AI. This is your fourth equation. So PGI is nothing but power generated in any plant is equal to lambda, that is incremental fuel cost, minus coefficients of cost equations, which are BI and AI. Is this clear?
Yes, sir.
Okay. So this is what we have done so far. We have taken cost equation, we have taken incremental fuel cost equation, and then we have taken coordination equation. Equated those two, and then we have realized the expression for PGI in terms of lambda, AI, and BI. So this finishes the stage 1. Now let us look into some problems over here. Have you got any doubts so far?
No, sir.
No, sir.
Okay. Shall we continue? Hello,
Yes, sir.
are you able to hear
Yes,
me?
sir.
Okay. So here, let's start with the first problem. The problem says the fuel cost of 2 units, 2 units means 2 generating units, are given by the following equations. See, before starting with the problem, I just want to tell you one thing. There, he has used F1. In some textbooks, they will use C1. For the fuel cost, some textbooks write it as F. Some textbooks, they write it as C. So both mean one and the same. So F1 is given by 1.5 plus 20 Pg1 plus 0.1 Pg1 square rupees per hour. F2 equal to 1.9 plus 30 Pg2 plus 0.1 Pg2 square rupees per hour. Then you have find optimum schedule. PD is equal to 200 megawatt. So in this particular problem, they have given the fuel cost equation for both the power plants. They have given the total load demand, which is 200 megawatt. You are supposed to find the optimal schedule. This means there are 2 generating plants feeding a total load of 200. These are the 2 equations available. You will have to find the optimal schedule. Optimal schedule means how optimally the load is being shared among the 2 units, which means they should operate at um, least operating cost. So for that purpose, we are going to use the coordination equation over here. Coordination equation always says the first derivative of the cost with respect to power of all the plants are equal to lambda. We are using that definition here. So I write df1 by d. See, instead of writing pd1 all the time, I straight away write p1. Both are the same. So df1 by dp1 is equal to df2 by dp2 is equal to lambda. Have you understood? Have you understood?
Yes, sir.
Okay. So what I have to do right now is I am given with f1 and f2. I have to find df1 by dp1 and df2 by dp2. I have to just differentiate f1 and f2 with respect to p1 and p2 individually. So take the first equation. In the first equation, if you try to differentiate f1 with respect to p1, you get 0.2 pg1 plus 20. I hope you people have not forgotten the differentiation. And df2 by dp2 is equal to 0.2 pg2 plus 30. Have you understood how we got df1 by dp1, df2 by dp2? Can I proceed? Hello? Hello?
Yes, sir.
Hello?
Yes,
Have
sir.
you understood
Yes,
the
sir.
equations? df1 by dp1. Okay. Now what has to be done as per coordination equation? We have to equate both those equations. df1 by dp1 should be equal to df2 by dp2. We'll do that. So 0.2 P1 plus 20 is equal to 0.2 P2 plus 30. Rearrange the equation. You get 0.2 P1 minus 0.2 P2 is equal to 10. This is your first equation. Second equation is always power balance equation. Am I audible?
Yes, sir.
Hello? Hello?
Yes, sir.
Am I audible?
Yes, sir.
Okay.
Yes,
So
sir.
0.2 P1 minus 0.2 P2 is equal to 10. Then we have power balance equation. Okay. Power balance equation is always total power generated is equal to total power drawn. In this case, losses are not there. So P1, totally 2 plants are there in this problem. So P1 plus P2 is equal to total power demand. In this problem, they've given 200 megawatts as the demand. So P1 plus P2 is equal to 200 is the second equation. First equation is coordination equation. Second equation is power balance equation. So there are 2 variables, there are 2 equations. You just have to solve these 2 equations to get P1 and P2. This is your optimal schedule, which is 125 megawatt and 75 megawatt. And whenever you're asked to find the optimal schedule, you should find P1, P2, and also find lambda. So lambda, you are going to find lambda by using the expression for incremental fuel cost equation. So either substitute in dC1 by dP1 or substitute in dC2 by dP2 because both are equal. So 0.2 P1 plus 20. Lambda is equal to 0.2 P1 plus 20. So I have got the generation P1, which is 125. If I use 125 there, so it becomes 0.2 into 125 plus 20. So you get lambda is equal to 45 rupees per megawatt hour. I already told you, whenever it is incremental fuel cost equation, the unit is rupees per megawatt hour. So this is how we get P1, P2, and lambda. Is the problem clear?
Yes, sir.
Okay, this is how you solve the problem on one type of problem on case one. You are given with two plants. They'll either give you cost equation or incremental full cost equation. You just have to use two equations. One is coordination equation. Second one is power balance. Use them, find the variables P1, P2. Then you have to find lambda. Do you want me to repeat first problem or shall I go to the next? Hello? Should I repeat first problem or go to the second problem?
You can proceed, sir.
Okay, fine. Okay, here, see in this particular problem, I have not given the complete statement of the problem. Straight away I have written the given data. So it says the incremental fuel cost in rupees per megawatt hour for a plant consisting of two units are given by dC1 by dP1 is equal to 0.2 P1 plus 40, dC2 by dP2 is equal to 0.25 P2 plus 30, and the demand is 150 megawatt. So in order to save time, I have not given the statement here. We are supposed to find economic load sharing. See, always remember optimal schedule, economic load sharing, all these terms mean one and the same. Second part is to find lambda, which is incremental fuel cost. Third part is saving compared to equal sharing. What is equal sharing? What is savings? We'll see that later. So far, by the experience with the first problem, we know how to find P1, P2, and lambda. Let us just do that here. So what is supposed to be done now? Mathematically, what is supposed to be done? Hello?
Equate both equations.
Yeah. In the previous problem, they had given you cost equation. So we had to find incremental fuel cost equation by taking first derivative. But here straight away has given you incremental fuel cost equation. Equate them. So you have 0.2 P1 plus 40 is equal to 0.25 P2 plus 30. Equate them. That is nothing but your coordination equation. And then power balance equation is P1 plus P2 is equal to demand. Demand is given as 150. So solve them. You'll be getting P1 and P2. So after solving that, I'm getting P1 and P2 as 61.11 and 88.88 megawatts. Then already you know how to find lambda. You just take one of the coordination equation, one of the incremental fuel cost equation, substitute the value of P over there. So here I have taken the first one, 0.2 P1 plus 40 is your first plant equation. And in case you want to go for second plant, that also can be done. You just have to take 0.25 P2 plus 30, substitute for P2 over there. You'll be getting the same values. So 0.2 into 61.11 plus 40, which is 52.22 rupees per megawatt hour. This is your lambda value. The third part is savings. See, he is talking about he's asking you to find the savings compared to equal load sharing. What do you mean by equal load sharing? What do you understand by the term equal load sharing? Anybody?
When lambda is equal to incremental fuel cost.
That is optimal load sharing. What is equal load sharing? In this problem, you are given what is the demand? What is the demand? What is the load demand? Hello? What is the
The
load demand?
61 megawatt.
150.
The P1
No,
and
no, no.
P2.
Load demand. 61.11 and 88.88 are the generation of the power by respective plants. What is the total load demand on the system?
150.
What is the load being? 150. So 150 is the total load demand. You are having two plants. Then how do you share the load equally among them? How do you share the load equally among those plants?
The
Increasing
P1
the
plus
generator.
What is the respective share? See, there are two generating plants. Demand is 150. How do you share them equally?
1:1 ratio.
75.
75. 150 divided by 2. Two plants are there and 150 megawatt is there. You have to share equally. 150 divided by 2 for each of the plants. 75, 75. This is what is equal load sharing. The given load demand you are going to divide among the given set of units. That will give you equal load sharing. Two plants are there here. 150 is the demand. 150 divided by 2, which is 75. This is equal load sharing. Whatever you have calculated till now is economic load sharing, wherein you have got 61.11 and 88.88. They are called economic load sharing values, which are based on coordination equation. But this is equal load sharing. Now we have to find out the difference between the two and whether we have saved some money by going for economic load sharing compared to equal load sharing. That's what we are trying to understand. And for that, there is a direct formula for finding the savings. That is given by integral of lower limit you are having P1, upper limit you are having P equal. P equal means equal load sharing value. dC1 by dP1, dC1 by dP1, dP1 plus integral of lower limit you are having P2 and upper limit you are having equal load sharing value dC2 by dP2, dP2. So what I'm doing here is, in the lower limit, I'm taking P1 which is 61.11 and upper limit is nothing but equal value which is 75 and dC1 by dP1 equation I'm writing here 0.2 P1 plus 40 plus second integral lower limit will be your P2. What is your P2? 88.88. Upper limit is equal value which is again 75 and I'm writing within the integral 0.25 P2 plus 30. If you do this integration, you'll be getting your savings value. Is this clear? Is this clear? Hello? Hello?
Yes, sir.
Have you understood this? This is a direct formula. We have another method also available when cost equation is given in the problem. When incremental fuel cost equation is given, this is how we approach. Don't worry about all methods. One by one, we'll be going step by step. Right now, just try to tell me whether you have understood this. Shall I go to the next sheet?
So,
Yes, sir.
yes, sir.
Yes.
Okay. So here I'm showing you the steps for integration. After doing the integration, I get the value as 43.92 rupees per, sorry, it should be rupees per hour. It's not rupees per megawatt hour, it should be rupees per hour. 41.92 rupees per hour. Similarly, we also try to calculate savings in rupees per day. Per hour, if it is 41.92, per day it should be 41.92 multiplied by 24. This finishes the calculation of savings in rupees per hour and rupees per day. Have you understood the problem?
Yes, sir.
Okay. Shall we go to the next problem, or do you want to just work out first and second problem? Do you want to write down? Because since it is online session, like offline session, we can't go fast here because different varieties of problems are there. We can't just hurry over here. So what do you want to do? Do you want to go through the first and second problem? Should I give you time, or should I go to the next problem?
Want to write.
Please tell me. Okay, fine. I'll share the screen for the first problem.
Okay.
Please make a note. And again, I'm repeating, please don't watch this like a movie. This is a mathematical subject. You have to solve, then only you'll be confident. Have you finished writing?
No, sir.
Yes, sir. No, sir.
Okay, I'll wait. Shall I go to the next page?
Yes, sir.
Yes, sir.
Okay. Is it over?
Yes, sir.
Shall I go to the next page?
Yes, sir.
Is this over?
Yes, sir.
Shall I go to the next page? Shall I proceed? Anybody still writing? Have you finished writing?
Yes, sir.
Yes,
Have you
sir.
finished writing? Or shall we wind up today's class?
Yes, sir.
Rest of the problems
Yeah,
will
we
continue in
can.
the further classes. And in case you're having any doubts, you can call me and ask.
Sure, sir.
Okay, if there is no clarification, you can exit the meet.